Hello everyone, welcome to this video. In this video we shall be looking at the proof of this theorem which we have just talked in the previous video. So according to this theorem, the operators we have defined as t positive, t negative and b, they are all bounded and self-adjoint operators. So we need to prove this thing in the first part. So let's have a look here. For the first part, because the operators b, t positive and t negative, what are they? They are the linear combinations of the operators b and t. So let's have a look how. B is the positive square root of t square. T positive is half time of the operator b plus t, and t negative is half time of the operator b minus t. So all of the three, b, t positive and t negative, they are the linear combination of the operators b and t, and hence they are self-adjoint and bounded. Why? Because both b and t, they are bounded as well as self-adjoint. So their linear combination is also bounded and self-adjoint. So therefore the operators b, t positive and t negative, they are self-adjoint and bounded. Okay, so for the second part of the theorem here, they say we have the operator b, t positive and t negative. All the three operators, they commute with every bounded linear operator that t commutes with. So suppose t commutes with s, right? So in that case, this s would commute with b also, it would commute with t positive also, and it would commute with t negative also. So this is what this theorem says. And in particular, if that is so, because t commutes with t, so therefore it would commute with b, it would commute with t positive, it would commute with t negative, and so all of them, they commute with each other. So let's prove this thing. Let's prove this b part over here. So we suppose that s is such operator such that it commutes with t. So now we wanted to prove that sb is equal to bs. One thing, we wanted to prove that st positive is equal to t positive of s, and we wanted to prove that st negative is equal to t negative of s. So we wanted to prove all of these three things over here, right? So we for that we consider this thing, we consider this t of ts. So when we just write it without bracket, so it would be tst, right? On the left hand side, this would become t square s, right? And we could commute this thing, because we know by this property of commutativity here, this ts is nothing but equal to st. So we could open up the brackets, and this thing would then become st square, right? So from here, if you remember, what was your b? Your b was the square root of t square. If that is so, if the square of this thing commutes with s, if this square commutes with s, b would also commute with s. Why? Because we have a theorem and a result over here that every positive bounded self-adjoint linear operator that has a unique positive square root which commutes with every bounded linear operator which commutes with a given operator. So that means whenever any bounded linear operator commutes with the given operator, its square root would also commute with it. So here in this case, because t square commute with it, so therefore t the square of so this would imply t square square root would also commute with s, right? And what is this t square square root? It is nothing but b. So you have bs is equal to sb over here in this case, right? Moreover, for the next operators, let's take this thing t positive of s. So let's apply the definition of t positive. It is half times of b plus t, right? So let's open up the bracket. So it is half times of bs and ts. Now bs commutes, b commutes with s. So you could write bs as sb, right? No problem in that. And we have by assumption assumed that ts is equal to st. That means s commutes with t. We already know that. So now you could take this s outside, both these s outside the brackets, so that you have s multiplied with half times of b plus c. Now what is this thing? This is again the definition of t positive. So you see, we started with t positive s and we landed at s t positive. So we have this second result over here for this part. For the next part, let's take t negative of s. It is very similar to the previous one. Now we'll just apply the definition for t negative. So it is half b minus t. Again we'll multiply by s inside and then commute both of these quantities and then take s again outside. So it is again the definition of t negative. So in this case you have this as the final result, right? So this is the proof for the second part. Now let's move on to the third part. Here in the third part, they say E commutes with every bounded self-adjoint linear operator that T commutes with. In particular, ET is equal to TE and EB is equal to BE, because both T commutes with T, right? And you also know B commutes with T. So E also commutes with E commutes with every bounded self-adjoint linear operator that T commutes with. And if you remember, what was your E? E was a projection of the given Hilbert space onto the null space of the operator T positive. So basically this image space, that was nothing but the null space of this T positive, right? So this was the projection operator that we were dealing with. Now we wanted to prove the commuteness of this operator E with whatever operator that commutes with T, right? So let's proceed. So in this case, here we assume that S is such operator which commutes with T. It is bounded as well as self-adjoint linear operator, right? So we assume that it commutes with T, so that means Ts is equal to St, right? And in this case we wanted to prove that, so this operator S now commutes with E also. So we wanted to prove Es is equal to Se, where what is E? E is the projection of the given Hilbert space onto the null space of T positive, right? So for that, in order to prove Es is equal to Se, we would like to have certain results beforehand before moving on to seeing the commutativity of Es, right? So let's first of all see these things. If we take some element x from the given Hilbert space H, then this E would map that particular x to y, where y is present in the null space of T positive. So that means you have taken this x from the given Hilbert space and you are mapping it to the corresponding null space of T positive, that is y space, right? So that is the terminology here that we are using. So here for every x which is present in the Hilbert space, we have some y in the null space which we could write as Ex. So this is a member of capital Y, which is the null space of T positive, right? So if that is so, if y belongs to the null space of T positive, so that means when you apply T positive onto y, you would surely get 0. This is according to the definition for the null space, right? So that means T positive y, that is equal to 0. And if you take S T positive y, so that means now we have proved that this thing is nothing but 0. So you have 0 in place of this thing, and what is S of 0? S being a linear operator would surely give you 0 here, right? And moreover, by our assumption that Ts is equal to St, we have assumed that S commutes with T, and from the part B, because S commutes with T, it would also commute with T positive according to part B, right? So we can use this thing, we can use this thing for our proof, right? So using both of these things, let's see what do we have here. We wanted to have T positive S E x with S. Now Ex is nothing but your y, right? And now also you could write T positive S as St positive using this above result, right? So using this result here, your T positive S is St positive. And what is your St positive y? Your St positive y is nothing but 0. So using this thing here, your St positive y is 0. So that means you have obtained T positive SEX as equal to 0. So what does this imply? It implies that whatever is inside of T positive, that belongs to the null space of T positive operator, which is nothing but the Y space, right? So this SEX that now belongs to the null space of T positive, right? And moreover, this E projects H onto Y. So therefore, using the properties of projection, now because this SEX that is a member of Y, so it would surely project all the elements of Y onto Y. So that means it would act as identity on all the elements of Y. So that is why if you apply E onto this element here, you would get it back, right? Let me write it down here. So E would act as an identity on the elements of Y, on the elements of Y. We have just proved that SEX, that is an element of Y. So when you apply E onto this element, it would give you the same element back, right? Now if you look at this thing more closely, if you take X as any arbitrary element from H, in that case these operators, they are equal to each other. ESE, that is equal to SE, right? So this is one thing that we obtained from here. And moreover, you know, every projection is self-adjoint as well as idempotent. So that means E is also self-adjoint, and we have assumed that S is a bounded self-adjoint linear operator. So S is also self-adjoint. Both E and S, they are self-adjoint in nature. If that is so, if both of them are self-adjoint, so that means that E star, that is equal to E, and S star, that is equal to S only, according to the properties of self-adjointness. So we start with ES, and we wanted to prove that this is equal to SE. So you could write E as E star and you could write as S star. No problem in that, because both of them, they are self-adjoint in nature. And according to the properties here, you know, A B star, that is nothing but that is equal to B star and A star. So using this result here, these operators, they change their order when you open up this star thing over the bracket. So here you could combine the star, so you have to reverse the order, so it is SE star, right? And now you know this SE is nothing but ESE. We have just proved it over here, right? So using this result here, this SE is ESE, so you have ESE star. So now you could again open up this star in the reverse order, so it is E star, S star and E star. And what is E star? That is E only. S star, that is S only. E star, that is E only. Why? Because they are self-adjoint in nature. And what is ESE? Your ESE is nothing but SE. So from here you see, you started with ES and landed at SE. So that means they commute. Both E and S, they commute with each other. And this is what we wanted to prove here in the C part. For the D part, for the proof of this D part, we have to go on to the next video. Well, that is it for this video. Thank you for watching.